Okay, there's one more section to talk about before we end up taking our Chapter 7 test, which is, I know, what you're all super excited for. Anyway, we're going to discuss a very particular type of logarithm today. That logarithm is the natural logarithm. Now, this logarithm, excuse me, is primarily based on the number e, and we'll talk a little bit more about that. E is an irrational number, kind of like pi in a way. How pi is used a lot for like circles and stuff. E is used for exponential equations. It is like the quintessential exponential number. It's like 2.7 something. Don't worry about that too much because we're just going to use it in the calculator. But E is a number. Keep that in mind. Yeah, so here's another slide telling you a little bit more about it. It says a mathematical constant, meaning, again, it's just a simple number, and is the base of the natural logarithm. So when we use natural logarithms, we are talking about E, and when we're talking about E, we're talking about natural logarithms. They're certainly they go together. They work together. When we do these equations, we're focused primarily on them. So it's kind of like your regular logarithms, but it was a little bit of a difference. Let's see. The natural log function. Okay, so the natural log function is f of x equals ln x. So ln for natural log, even though I know it's kind of backwards. Ln instead of nl. It's ln. It's probably ln because I guess the original translation of it was probably log natural and whatever language it originated in. But anyway, it's ln x. That's your natural log function. You'll see that button on the calculator too. Let me see if I can pull mine up just real quick. Right, natural log button. Yeah, you can see it down here near the bottom. Next to the 4, right by the log button. So it's there. It'll be used. It's the inverse of the exponential function with the natural log base, which is the exponential function is f(x) equals e to the x. Okay. Again, e is that 2.71828 number, but we're not really going to worry about this too much. Just know that it is a number, but we'll really just use the calculator. We'll just type e in the calculator, and we'll make sure we type it in right because there's a lot of looking e's on the calculator, but we want to make sure we use the right one. I'll show you that when we get into an example. So the properties of our logarithms are very similar to the properties of our properties of our natural logarithms are very similar to I'm watching the Tottenham Leicester game right now, so I apologize. They scored a goal. Anyway, what was I talking about? Yes, the logarithms properties that we discussed about before, the same exists for the natural log properties as well. So we talked, if you remember way back a couple videos ago, log of any base being of 1 would always equal 0. And that's obviously true with natural log too. Natural log of 1 equals 0. Now, the thing about natural log is there is no base number for these. It's just a natural log. So there's no like little number that's going to be there, which is kind of nice not to have to worry about that. But yeah, this says the same thing that this property says. If you have a log of 1, it's always going to be equal to 0. And remember, natural log and e are always going to cancel themselves out. Now, when they cancel out, they don't like leave you with 0. They leave you with 1. Okay? That's very important to remember. People think when they cancel out, you're left with 0. That's not the case. Like, for instance, if you have the fraction x over x, well, these x's cancel out, but this fraction doesn't equal 0. This fraction equals 1, right? Because it's 1x divided by 1x. So these 1s are kind of always there. 1 over 1 is always 1. So keep in mind, when I say canceling out, it's always going to be equal to 1. Same is true here. When the natural log and e cancel out again, you're just going to be left with this x. And so that's just going to equal x because these cancel out. Same thing down here, e and natural log cancel out. And those are very same properties we saw with logarithms as well. Okay, so let's just simplify real quick just to make sure we understand the whole process of what cancels out and what exists still. So In A, notice we have natural log of e to the 0.15 t power. So since the natural log and e are together, right, they immediately are going to cancel each other out, leaving you with just the 0.15 t. All right. Now look at B. B's a little different because we have e and natural log, but they're not quite together yet because there's this 3 in between them. So we do need to relocate that 3 before the e and the natural log will cancel out. Now, if you remember back when we did regular logarithms, this p number, if it's multiplied to the logarithm, is the same as if that p number was the exponent, because remember we took the exponent and moved it to the front and it ended up over here. Well, as you notice, that's the same thing with our natural log. That 3 is in front, and if we want to relocate that 3 to the top, we can. So that 3 belongs as an exponent up there. It's the same thing that we were talking about when we talked about this property. So if we do that, then this is the same as e natural log of x plus 1 to the third power. If I can kind of make that look like a 3, we're good. All right. So now you see the e natural log are together. Those are going to just cancel out, and we're left with the result of the x plus 1 to the third power. So just be aware of that. You know, they're only going to cancel once they're next to each other. If you got that 3 or something in between them, make sure you do something with it. In this case, that 3 that's being multiplied to the front of the log can get moved back into the exponent spot. So remember that property. And down here, another similar property to logs. Remember when we had logarithms? Just give you an example for a second. If we were taking logarithms and adding them, remember we actually multiplied these values within them to make, you know, the log 4 of 100 in this case, because 25 times 4 is 100. And that idea is going to be the same for regular logs as well, or natural logs. So if we're adding logarithms, we can scratch that. I forgot that this had e in it. That property is true, but that's only true if we had like log of 5x plus, or natural log of 5x plus natural log of like 2 or something. This would be the natural log of 10x, because 5x times 2 makes 10x, and that's totally cool. But I wasn't looking at the problem. This problem has e in it, and those e's are just going to cancel. So natural log of e to 2x power, those are just going to cancel out since they're good together, just leaving you with 2x. And here the natural log and e are going to cancel out as well, leaving you just with x. So essentially, it's just 2x plus x, which is 3x. But that property still exists, the part where you multiply them together. But that's not neither here nor there with this one, because the e's in the problem, the e is going to cancel out the natural log. So, yes. So there's your results. All right. Now, let's talk about this formula. So this formula is related to compound interest. Now, you may or may not have talked about the compound interest formula in the past. The regular compound interest formula is this. You have A, which is your final amount, equals P, which is your starting amount. It's kind of similar to the exponential growth problem or growth formula. It's 1 plus R over N to the N times T power, where P represents your starting amount, R represents rate, like 5% or 0.05. T represents time, like the X represented time before. The only real new thing between this formula and your original growth formula is the fact that we have this N. So, you know, A was used in the original formula, but we're calling it P in this one, but it means the same thing as the starting amount. The N is the new thing, and N represents how often it's compounded, how many times per year. So if it said, like, if it's compounded quarterly, for example, it would mean compounded 4 times a year. If it was compounded monthly, it'd be compounded 12 times a year, and you would use those numbers for N. Now, this formula, it's related to that formula, but it's for when it's being compounded continuously, which means kind of like nonstop. And that's where the E comes into play. So P will represent our starting amount. E is a number. Remember, it's not a variable. We are going to plug that into our calculator. R will represent the rate, and T will represent the time, just as before. So it's a very simple formula, but you have to know when to use it, because on the test, you're going to have times where you're going to need to use this compound interest formula, and then this compound interest formula, because they are sort of the same formula. It's just this will be compounded a particular number of times. You know, compounded monthly would be 12. Compounded quarterly would be a 4. Compounded daily would be 365. Compounded semi-annually would be 2. Oh, I unmuted my game. How did I do that? Here we go. All right, cool. Hopefully you didn't hear that, man. All right. Anyway, but when it says compounded continuously, the keyword continuously, that's your go-to. That's how you know it's going to be this formula. When it says compounded continuously. If it says compounded anything else, it's going to be this formula. All right. But we're primarily going to focus on this one right now since it's got the E in it. So what is the total amount for an investment of $500 invested at 5.2.5% for 40 years and compounded continuously? So again, it'll tell you continuously in the problem. That's your giveaway that we're talking about this formula. Okay, so A is our final amount. That's essentially our answer that we're looking for. P represents the starting amount. So we are starting with an investment of $500. So that's my P value. And then E, remember, is the 2.7 number. We're going to type it in the calculator. It's not a variable. That's something that's part of this function that we'll type in the calculator. R represents rate, and our rate is 5.25%. And just like before, we need to convert this from a percentage to a numeric value. So move the decimal 2 places left, and you get 0.0525. So 0.0525. And then 40 years, that's our T. So we're going to make sure we multiply by 40. So there's your formula. Now it's just a matter of typing this into the calculator. So let's get the calculator out. And so you can kind of see the answer there, spoiler alert. But anyway, let's type this in. We had 500. Now here's how you type E in, okay? So be careful, because there's a lot of E's. If you look at the natural log button by the 4, you see right above it, it says e to the x power. So we're going to hit second and then hit that natural log button, and it brings you e and it gives that exponent for you. So there's your e. Now you just type in the exponent. Our exponent was 0.0525 times 40. So we're going to put in that 0.0525 times 40. All right, and that should be good. And we get $4,083 and about 8 cents, which is what our answer was on our PowerPoint. So that's cool. So it's very straightforward. It's just a formula and plugging it in the formula. Just make sure you don't screw up the rate. Make sure you use the proper version of E in the calculator. As long as you do those things, it should be pretty much a walk in the park. So we'll do another one, just, you know, for some good practice. So what's the total amount for an investment of $100 invested 3.5% for 8 years and compounded continuously? So again, continuously tells us we're using that formula. So A, which is our final amount, which is what I'm looking for, says what is the total amount? That's what A will eventually be. P is our starting amount, and we're starting with $100. E, remember E is part of the formula. R is my rate, which is 3.5%. Now 3.5% as a numeric value is move that decimal 2 places. You get 0.035. So 0.035 times T, and we're talking about 8 years here. So there's your formula. Now I'll just plug it into the calculator and see what we get. So we started with 100. Make sure you type in E. Remember, E is second, and then the natural log button gives you E with that decimal. And it was 0.35 or 0.035? 0.035 is my rate times 8 for 8 years. And we get 132, is it dollars? Yeah, doesn't seem like that much, but it is. $132.31. So obviously, if you invest more money for a longer period of time, you're going to make more money. But if you invest only a small amount of money and don't keep it in there very long, you're not going to make nearly as much. So it's important you leave if you're going to invest money, you leave it for a long time, for like retirement savings or something, or invest a pretty good amount to begin with, because the more you invest, the faster it'll be able to grow. So just a couple things to keep in mind. Now, there's one more thing I want to do before I leave you guys in this video, and that's the equations. So talked a little bit about that already, the single logarithm. Let me just remind you. So so what I would do here is move this 4 to the top up here. So it's the natural log of 3 to the 4th power plus the natural log of 6, which 3 to the 4th power is 81, and natural log of 6, well, that's 6. So remember, if you add logarithms, you would multiply these together. So, you'd have 81 times 6, and that would be a thing. I do the same thing here, move the 2 to the top, and then you're multiplying the 3 squared, which ends up being 9, times the 4 times the y. Because if you're adding all these together, you're multiplying all these different values together. And if you are subtracting, then you're dividing. So, I'd move that 2 to the top. This would be the natural log of, it looks like an h, the natural log of 3 to the 2nd power, which is 9. This is still the natural log of 10. So this would end up being, the natural log of 10 divided by 9. Remember, subtracting is division, adding is multiplication. If you're wondering number 2 should be, so if you have the natural log of 9 plus the natural log of 4 plus the natural log of y, then you're doing 9 times 4 times y, which makes the natural log of 36y, if you multiply all of them together. So just keep that in mind. Same rules as before. But now let's solve these equations. Let's go ahead and do this first one, right? So we have e to the x power equals 23. So our goal is to solve for x, of course. But to get x by itself, I need something that cancels out e. Well, we know what cancels out e, right? We know natural log cancels out e. So kind of like similar to the logarithm problems we did before, or I guess the exponential equations we did before, but we use logarithms, is we're going to throw in log on both sides. But it's not going to be the regular log, it'll be natural log. Since we're talking about e, we're going to put the natural log on both sides. So we still have e to the x equals 23, but I'm throwing in a natural log on both sides. And why do I do that? Well, because the natural log and e are immediately going to cancel out, leaving me with just x on this side equals to that natural log of 23. And sometimes you can leave your answer like this. You can leave your answer as the natural log of 23, but sometimes people want you to actually write out the decimal, and if you want to do that, you can just type in the calculator. It's not going to be too big a deal. So it's 3.135, but yeah, sometimes you can just leave it as natural log 23. I don't think anybody's going to be too heartbroken about that. So number 2, e to the x plus 1 equals 30. So again, I need to focus on canceling this e out. So to do that, again, I'm going to throw the natural log on both sides of the equation, just like I did in the last example. So it's the same problem. It's still e to the x plus 1 power equals 30, but I've got the natural log in front of both. Now, the reason that's useful is because the natural log and e are going to cancel and leave us with x plus 1 equals to the natural log of 30. And if we want to answer this, we just subtract 1 on both sides. Now, be careful, because I can see people doing this already. The natural log of 30 minus 1 is not the natural log of 29, okay? The natural log of 30 is some random number. Instead of converting it to a decimal yet, I'm just leaving it as that. So natural log of 30, I should really put parentheses on this so that you understand that, that 30 is with that natural log minus 1. Okay, so that's going to be another number, natural log of 30. minus 1. And if you want the actual value, you can do that. Type in the calculator, natural log of 30 minus 1. And you get 2.4. Now, if you went ahead and found the natural log of 30 first and said, oh, look, that's 3.40 or something, and then went ahead and subtracted 1 later, you can do that. It's still going to be the same number, the 2.4. Just don't, for the love of whatever, okay, do not say natural log of 29. Do not try to do that. That's not how that works. Okay. All right, so what if we have the natural log of x, right? Natural log x equals 5. Now this is where it gets a little more interesting. Not any harder, but a little more interesting. Because to get the x by itself, I need to cancel out the natural log. So what cancels out the natural log? Well, e does. But here I am talking with my hands as if it makes a difference, and I'm just throwing my pens everywhere. But the way you use e is going to look kind of funny because e is a base of an exponent. So how you're going to use e to cancel out the natural log is this. You're going to have e, and then the natural log of x will be the exponent here on this side. And it'll be the same thing on the other side. You're going to use e as the base and make 5 the exponent. That's how you use e to cancel out natural log. It looks really goofy, but that's how it works. When you throw e in, everything becomes an exponent for e. And that's not too big a deal. You know, e and natural log immediately here are going to cancel, so we have x equal to e to the 5th power. And that's your answer. And you can type that in to get whatever decimal that equals. E to the 5th power. So second log, it's e, and then to the 5th power. You get 148.41, and that's the answer. Which, by the way, if you want to check that this works, remember it was the natural log of x, so if that's x, then if I do the natural log of that answer that I just got, it should be 5. And it is, right? So you can kind of plug that in, make sure it works. So another thing to note and keep in mind. All right. Now this is supposed to say, natural log of negative 5x. Keep it. So that's a slight mess up without the parentheses, but we're good. So how are we going to solve this? We have the natural log of negative 5x equals the natural log of 4 minus 3x. Now, it seems complicated, but it's actually pretty easy. If this natural log is equal to this natural log, then doesn't that mean that this is equal to this, right? That negative 5x is equal to 4 minus 3x? Don't those have to be equal to each other if the natural logs are equal to each other? And the answer is yes, that's the case. So there you go. Now you've got this equation. You don't even really need the natural logs, because even if you did put e on both sides, these would just cancel out, and you'd be left with that negative 5x equals 4 minus 3x anyway. So negative 2x equals 4, and so x equals negative 2. All right, and let's do one more here. So here's an interesting, again, this needs parentheses. It's supposed to be negative 9x like this. Here's another interesting thing. So rather than trying to move this to an exponent up here, let's go ahead and cancel this negative 8 out. So notice that this negative 8 is being multiplied to the natural log, right? Well, if I want to get rid of the negative 8 just entirely, then I can just divide this side by negative 8. If I do that, then I'll cancel it out, but I have to do that to this side as well. So it's one of those things that you might not have thought about, but you might have, I'm not sure. But if you do, then this equation is now the natural log of negative 9x equal to 1. Because negative 8 divided by negative 8 over here is just 1. So that's something you want to do. If you can divide this number, do it. Rather than moving it back up here, which you could, but it would be easier if you can just get rid of it now, rather than having to move it and get rid of it later. So if you can get rid of it now, do so. And then we can do that by the division. So just like before, if I want to cancel out the natural log, I'm going to make these things exponents. The natural log natural log of e to the natural log of negative 9x equals e to the first power. So that's going to immediately cancel, and we have negative 9x equal to e to the first power. So just divide by negative 9, and you've got your answer. X equals whatever e to the first power divided by negative 9 is. And again, you can just type that in the calculator. All right, that's going to be it for this video. I apologize if it's kind of long, but I did want to make sure I had everything in it. We might have had 2 days in class to work on this. But the equations are very, very important. The equations that we just did and the compounded continuously formula are two very, very big things. So hopefully that helps. I'll see you guys in the next one. Be ready. A chapter test is coming up probably next week. All right. Bye.